Morning. Welcome back. So today the first talk will be given by NABER. He's going to talk about structure of singular sets and energy identity of harmonic maps.
Okay.
Please.
Well, thank you very much. To begin, thank you for inviting me to this conference and honor my advisor, Gong Tian, without Gong Tian, apparently. So for a 30-minute talk, what I basically did was take my talk and I tried to throw out everything that was too easy and everything that was too hard. So with a little bit of luck, we've got the right little portion in it, but I'm not really convinced it's going to flow all that well. We're going to have to cross our fingers and see. So what I want to talk about in today's lecture is a type of singularity formation that can occur for nonlinear harmonic maps. And actually, as a brief overview, I mean, the nonlinear harmonic map isn't so important. We talk about singular sets of nonlinear equations all the times in geometric analysis. But what I'm talking about here isn't the singular set of a fixed solution to some nonlinear equation. Well, what happens is that if you take sequences of solutions, it turns out that singularities can form on bigger sets than they can actually exist on any fixed solution of your guy. Right? So this is a very different type of singularity that's kind of occurring especially if you're considering moduli spaces and compactness and things like this, or any sort of sequence. This is how things go wrong inside this. That might be more than just what happens on a fixed guy. And it turns out that you can quantify sort of what happens in these sort of blow-up sets by something called the defect measure, which we'll sort of go through and try to understand. And similar sort of analogous things appear both for Yang-Mills and Einstein manifolds as we're going through. And actually, they probably appear for other equations too, but you have to write the right notion of energy. And sometimes people can, sometimes people don't. And then the energy identity is basically a conjecture that says that this defect measure, this thing that's capturing what went wrong for the sequence of solutions and how blow-up was occurring, should be precisely describable. We actually know what this thing looks like, and we know how to describe what its behavior is, right? And so we'll try to work our way up, try to stating this and stating the recent theorems, which is that it's true. Okay, so wait, wrong computer. There we go. Okay, outline. So first, let me point out this is all joint work with Daniela Valtorta, and we will start by discussing some examples of nonlinear equations. And that way, if you're not familiar with nonlinear harmonic maps, the broad point here is that if you're familiar with anything in this sort of broad scheme here, really there's morals there, so you can blur your eyes a little bit, and it doesn't matter that much when we're kind of going through all this. And we'll focus most of our time on nonlinear harmonic maps itself. And we'll talk about a bunch of examples. I actually won't talk about regularity or singularity properties. I cut all that out for half an hour purpose. But we will discuss bubbles and defect measures. So this sort of blow-up behavior. Mostly, I will try to avoid technical definitions in this talk. We will define things through examples. I'll write down an example. We'll see a behavior that can occur, and I'll say, yeah, there's a technical version of this that kind of exists in general, and maybe make a word about it or two about it, maybe with one exception. And then I'll try to state for you what the energy identity is, and I highly doubt I'm going to give you a proof outline by the time this is done. So let's just start with some examples of nonlinear Laplacians that can kind of occur in our business. Probably one of the popular ones are minimal surfaces, right? And so the point is you can view the mean curvature here as basically being the Laplacian of the coordinate functions, right? And this is nonlinear because it's the Laplacian of your submanifold, which itself is spinning and moving around. So there's some interdependence of what your Laplacian is and what the actual submanifold is. And so this is really an example of a nonlinear Laplace equation that's being solved. Einstein manifolds are another good example. So the Ricci curvature here should really be understood as being the Laplacian of the metric. The actual Laplacian of the metric vanishes because, for silly reasons, almost by definition. But sort of mod gauge, one understands the Ricci curvature as being the right replacement for the Laplacian. And actually, in like the right coordinates, it's literally that, with some nonlinear terms that appear. Yang-Mills, once again, another example of a nonlinear Laplacian. Right, so in this case, you should be viewing the curvature. The right way to view the curvature of a connection should be as basically the derivative of the connection. Right, you're going one derivative up. It's a derivative mod gauge, hence all the other weird terms that are floating around there. But intuitively, you should understand it as the derivative of a connection. And therefore, a Yang-Mills connection is the divergence of the curvature vanishes, hence divergence of the derivative of the connection vanishes, so Laplacian. And of course, when you write this in coordinates, there's all kinds of nonlinear terms that appear for this, but that's the right way to view it. And a bunch of others, right? We've got free boundary problems, nonlinear harmonic maps, biharmonic maps. Actually, it's a double Laplacian, but whatever. Q-valued harmonic maps, there's parabolic versions, there's nodal problems, and these all kind of have very similar behaviors in the end when so a lot of that sort of tools and techniques that get built for one of these actually work for others. It's actually helpful to think about all of them at once, because very often something you try in one, you'll realize very quickly in another one it's obviously wrong, whereas maybe it's not so obviously wrong in the when you were thinking about the moment. So it's very helpful to think about all of these things at the same time, actually. Okay. Background. So what is a nonlinear harmonic map? So what do we start with? We start with a function from a ball, let's say, and some manifold, but you can call M here can be Euclidean space. This doesn't matter. Now, the tricky part here is that it's a mapping from one manifold to another manifold N, and this target N not being Euclidean space is the problem. So think of it as being a mapping from a ball in Euclidean space, if you want, into some manifold N. And so as an example here, right, we have the ball inside of Euclidean space, and it might map to the 2-sphere, which you can view as sitting inside the R3 if you want, right? So it's really a mapping into R3, just to make your life easy, but restricted to the values have to be inside the sphere. If we have such a mapping, just call it smooth for the sake of argument, we can talk about its derivative. And what is the derivative? The derivative, right, really maps something from the tangent space over here to the everyone can see it over here. So we have our two manifolds. We have our mapping U in between them. Take a point X. U maps to U of X, and the derivative of U maps a vector V, right, to du of V, which is over here. So it's really the derivative maps tangents over on M to tangents over on N over here. And if both M and N are Riemannian manifolds, the observation is that this is a linear mapping between two linear spaces, and we can look at norms. So exactly like you might do for a linear Laplacian, what we can actually do is look at its derivative, and we can look at the energy functional. So if we take our derivative between our two manifolds, we look at the norm of that linear mapping, we get some number, we square it, we integrate the silly thing, and we get a Dirichlet energy out of this, right? This is a very nonlinear energy, though, in this context, unlike like the linear Laplace case. And so to say that a mapping U is harmonic can mean one of three things. And it's interesting to point out these three things are all the same for if the mapping is into R, right, standard harmonic function. These three things are the same. And if it's not into R, they're wildly different objects, right? The worst version of a harmonic map is what we call weakly harmonic, and that's if it solves the Euler-Lagrange equation. So if we look at critical points of this guy, we get an Euler-Lagrange equation out of this. That means that we're solving literally the Laplacian of U. This A is to say the second fundamental form. If we embed it into some Euclidean space, you can write this in about 6 billion different ways. It doesn't matter. It's all equivalent. Then we get some nonlinear equation that gets solved. If you're a critical point, that's the Euler-Lagrange equation. And if you solve the Euler-Lagrange equation weakly, we call it a weakly harmonic map. On the other hand, and as a special case for the sphere, right, if we're mapping into the S2 thing inside of R3, then this is the equation that kind of pops out of it in the end, which is nice and clean and mildly entertaining. We call it stationary. There's actually a few ways of saying this, but I think that the easiest way to get our heads around it is if it's a critical point of the energy functional. So what's I think very counterintuitive if you're not used to the field is that these are not the same. Being a critical point of this energy functional does imply that you solve the Euler-Lagrange equation, but the other direction is not true. Right? Solving the equation is weaker than being a critical point of the energy functional. This is subtle because it's not true if you're smooth. Actually, if you're smooth, then solving the Euler-Lagrange equation will make you a critical point of the energy functional, but if you're not smooth, it's not true. You miss directions, as it turns out. So it is more fundamental to be a critical point of a functional than it is to solve the Euler-Lagrange equation, right? This is going to be the takeaway as we kind of move forward with all of this. In practice, this is how you build solutions anyways. You try to find critical points of functionals, and really the point is that's not the same as weakly harmonic anyways. It's not the same as solving the Euler-Lagrange equation. This is what you want to do. You get better control. And finally, you can be a minimizer of the energy functional. So certainly if you're a minimizer of the energy functional, you're a critical point of the energy functional, therefore a weakly harmonic function. But again, you're not true going that way, right? Being a critical point doesn't make you a minimizer. If you're a linear harmonic function, then this is literally, the energy functional is literally quadratic and non-negative. So a critical point is a minimum, right? So it's the same thing. But of course, in the nonlinear case, there's just absolutely zero reason for this to be true. And if n is r, they're all the same. But in general, minimizer implies stationary, implies weakly, but not the other direction. I'm not going to do this much because there's not time, but let me just sort of point out. If you're a minimizer, you're known to be smooth away from a codimension 3 set. This is Shane and Uhlenbeck. If you're stationary, you're known to be a critical point. If you're known to be smooth away from a codimension 2 set, there are at least smooth points of your solutions. Away from a codimension 2 set, this is due to Bethiel. If you're weakly harmonic, you're known that you don't have to be smooth anywhere. You can be discontinuous at every single point. This is an example due to Tristan Riviere. So they are very, very different objects from a regularity theory point of view, which is what we tend to like. Okay, let's do an example of a nonlinear harmonic map. So our easiest class of examples come from the following. Let's look at S2, which I'm going to view as being CP1, right? So what that means is I'm going to look at pairs of complex numbers, right? Not both zero, right? Z1, Z2. And I'm going to call them equivalent if they differ by complex multiplication of a fixed lambda, right? So this guy equals this guy over here, right? And that equivalence class gives you CP1, which is the same thing as S2. That's how I want to identify my S2 here. This turns out just to be convenient for our expressions. And now let's let P and Q be two homogeneous holomorphic polynomials on C2, right? So C2 is what the thing you quotient out by, right, to get your CP1. It's the bigger object. Degree D, same D, right? So it could be Z squared, or they could be Z1 squared, or Z1 times Z2, or whatever you want. And now let's note the following. We get now a mapping from S2 to S2 by doing the following. Take a point in S2, which is a pair of complex numbers, and let's map it to the pair, which is P applied to this pair and Q applied to this pair. And note that if P and Q are both homogeneous polynomials with the same degree, this is a well-defined map from S2 to S2, not just from S2 into C2. Because if I multiply both these guys by lambda, that means I'm multiplying these guys by lambda, and it pulls out to lambda to the d. And these are both multiplied by lambda, which pulls out to lambda to the d. So they both get multiplied by lambda to the d, which means it's the same. So I get a well-defined mapping from S2 to S2. And it probably won't take much to convince you because everything in the world here is holomorphic. This is a holomorphic mapping. And there's a nice theorem out there that basically just says you can compute that if your two Kähler manifolds and you're holomorphic, you have to be harmonic. So these are actually harmonic maps. So just as a dumb example here, right? Z1 squared plus Z2 squared, Z1 times Z2. I'll actually look at some specific examples of this in just a moment. These are all smooth maps, also kind of reasonable to point out. Also, I might point out that for harmonic maps between S2 and S2, if I at least insist that they're oriented on these two mappings, this is it. This is all of them. One more example. So there's another example that has a slightly different feel to it. So let's define U from R3, right? So whatever. So here's my R3, which looks suspiciously like an R2. And here's my S2, which looks suspiciously like an S1. And I'm going to take a mapping from R3 into S2 by just taking a point X and just projecting it into S2, right? X over norm X. Kind of the dumbest thing you might do as a mapping from R3 to S2. And it turns out this is not just a harmonic map. It is a minimizing harmonic map. Right? So this guy actually minimizes the Dirichlet energy from all of this. And note, of course, it's not smooth. Right? It's smooth everywhere except the origin because there is no projection at the origin into S2. So this is basically your easiest example of a minimizing harmonic map that is, as was sort of claimed vaguely in the last slide, smooth away from a codimension 3 set. Right? So a point inside of R3 is codimension 3. Right? So in general, there's theorems then that say that that's the worst that can ever really happen in some sense. You go to dimension 4, you might get some lines or some rectifiable one whatevers, but that's all that can really happen. How's everybody? No one's stopping me. Good. Making eye contact there, so that's good. Okay. All right. So more examples. You can get a bunch of examples from this by just doing the following. Get mappings from R3 to S2 by projecting and then composing with one of these. It turns out that those will all be harmonic too, but depending on which P and Q you pick, they'll actually either be weakly stationary or minimizing. So you'll get examples of all kinds of different harmonic maps this way, including some that are just weakly. And you can get sequences of stationary harmonic maps that'll converge to a non-stationary weakly harmonic map this way. So you'll see that being a sequence of critical points isn't preserved in the limits. Okay, how am I doing? What time is it? 45. You know what? I don't even know how I'm doing. I'm not quite sure how much time I have left here. Well, yeah, 15 minutes, right? I meant slide-wise. Okay, so defect measures. Okay, there's your two basic examples. I want to move our attention now to some singular types of singularities that can occur for sequences of nonlinear harmonic maps. So in the last example, we had these two-dimensional harmonic maps, and they were smooth, and we had a three-dimensional harmonic map, so from something three-dimensional into something else that had point singularities. And now I want to talk about sequences of harmonic maps and kind of ask what can go wrong inside the sequence. So specifically, our setup is going to be the following. We have some sequence of stationary, always stationary critical points at this point. Weakly harmonic will sort of never be considered in any of this. These are horrible objects. We'll consider a sequence of harmonic maps from some fixed guy into n, which all have a uniform bound on their energy. Right. So you're supposed to be a critical point of your energy functional. We're asking that energy be finite, whatever it is in this sequence. Interesting point, by the way. I think really good open problems here are sequences of maps where energy goes to infinity. This is one situation where essentially Ricci curvature knows how to control these guys, but no other nonlinear equation knows how to actually do this. There should be ways of saying stuff in limits, maybe with the slight exception of minimal surfaces in dimension 3. Mr. Coley-Monacosi can do this to some extent. So if, just for the sake of argument, all of our domains here are two-dimensional, like in our last example, they're two spheres, then we know they're smooth. So if this is a two-dimensional guy, you've got to actually be smooth, as it turns out. So a harmonic map from a two-dimensional guy into something else will be smooth. However, if we take a sequence of them, it may not. Things may start to blow up. It's not uniformly smooth. We don't know how smooth it is. We just know it's smooth. And so we want to know, how does that happen, is the first question. And so the basic example we're going to consider here is the classic bubbling. Okay, so here's our setup. So again, let's start with our CP1, our S2, which is being viewed as pairs of complex numbers. I'm going to write a map here from C, just a second, into S2. And the mapping from C into S2 is going to look as follows. In fact, it'll be a sequence of maps. So it'll be, we'll take a point Z, and we're going to map it to the pair, which is epsilon's just some fixed something here, epsilon Z. Right, so we'll look at epsilon Z over here. So let's think about this mapping for just a second real quick, right? So if we let Z itself be epsilon, or have norm epsilon if you want, so we're looking at the circle of radius epsilon here, then this is mapping basically to the point 1, 1. This is like some fixed circle on your two sphere. So this radius epsilon guy kind of always maps, roughly speaking, over here. No matter what epsilon is, once you've gone distance epsilon away from the origin, you've wrapped around like half the sphere in this example, right? So in small time, you've wrapped yourself halfway around your sphere. And on the other hand, oops, let's maybe not do that just yet. At 0, right, we're always at the point, so that's epsilon 0, which is the same thing as 1, 0, because it's equivalent, right? So this point here always maps to, say, the south pole. This ball here always maps to like this half sphere. And then once we move far out, some definite distance out here, this always maps, well, really, really close to the north pole, which is 0, 1. So this mapping is like a degree 1 mapping from C into S2. It just folds itself around S2, but it's doing it faster and faster as epsilon gets small. right? It does it like in time epsilon and length epsilon, and it moves halfway around the sphere. These are all harmonic maps because by the last examples, they're examples of these things, well, almost anyway. And let's make some observations. So first, independent of epsilon, these things all have the same energy, as it turns out. So they're wrapping faster and faster around the S2, but they're not doing it with energy blowing up. Their energy is actually exactly the same no matter what. Basically, the two-dimensionality of the C and the squared here balance each other, is what kind of happens. And on the other hand, if I actually consider this sequence and I take the limit, so what happens is epsilon goes to 0 here. Well, what's happening is that anywhere away from this epsilon ball, you're basically converging to just the North Pole out here when you go out. So when you take your limit, your F epsilon converges to some F naught, which is just a constant map. So we have the sequence of finite energy maps. They converge to smooth maps, for that matter, smooth harmonic maps. They converge to a smooth harmonic map, but they clearly don't converge smoothly, right? Because at the origin, you're getting this wraparound that's occurring faster and faster. So namely, the derivative is roughly like epsilon inverse at the origin. Always, it's kind of wrapping around. So this is how blowup occurs, right? Sequence, smooth guys, but blowups occurring at a single point. So if we want to understand what this blowup is happening and how it happens in general, there's actually a set of tools for this, namely defect measures. So the defect measure is the following. Consider a sequence of mappings. Actually, they don't really even need to be harmonic for some of the statements I'm about to make. They'll just be, it may not be as interesting if you're not harmonic. And you got a sequence of your stationary harmonic maps. They have bounded energy. Well, what do you do with a sequence of maps with bounded energy? Well, you can do a couple things. One of which is that you can take a subsequence that converges weakly in H1 to some limits, right? You can always do this. The other thing that's really instructive here is to take your energy here, which is some nice function, right? It's an L1 function, kind of by definition. But don't think of it as a function. Think of it as a measure, right? So these are the so-called energy measures of this guy. And the reason you want to think of it as a measure instead of a function is that we can also limit out this measure here. As a measure, we can limit it out. Because if these are just converging weakly in H1, but not strongly, then essentially the energy can drop in the limit, right? But this won't. So basically where this goes bad in the limit as a probability, a sequence of finite measures, it will be telling us where we lost energy in the limit. So we want to limit the functions weakly in H1, but we want to limit their energies as measures so that we don't lose what got lost in the limit. So after passing to a bunch of subsequences, that's what we do. Right? We go Fj, they converge to some F naught weakly in H1, so we get some limit function. And now our energy measures are going to converge to the following. They're going to converge basically, well, like all measures, it's going to have like a Lebesgue part and a singular part. And at least for harmonic maps here, this is going to break up into the energy measure of your limit plus something that's singular. So this is basically representing what got lost when we took this limit here. And that's what we call the defect measure. It's basically telling us how far away this is from converging strongly in H1, which is to say how much blowup is actually occurring in the sequence. Where's energy being lost? So if we go back to our old example from last time and just ask what happened there, we had our sequence of harmonic maps from C into S2, epsilon z, right? We had that the f sub j's converged to a constant, 0, 1. We already sort of discovered that before. And now if we look at the energy measures of these things and ask what's happening there, well, since you're converging to a constant away from the origin here, that's converging to something that's purely singular. Like you've got 0. But of course, these things all had integral 8 pi, was our statement from before. So, well, what we've got is a Dirac delta at the origin, 8 pi times the Dirac delta at the origin. So this didn't get lost. We see the blowup that occurred, the non-smoothness of our limits by looking at our limit Dirac delta measure from our defect measure out of all this. And note in this example, we had that the defect measure was concentrated at a point in R2, which was a codimension 2 set, so a point in 2 dimensions, codimension 2, and that's not random. So there's a theorem going back to Fengwo Lin that says that this always happens, right? So he said that take a sequence of stationary harmonic maps of bounded energy. Then this defect measure, which you get by taking your limits and looking at the singular part of the energy measure, is always n-2 rectifiable. Right? So not only is it n-2 dimensional, but it's actually got, it's almost like an n-2 manifold that's concentrated on. Maybe there's some holes in it, but it's got a nice structure on it. So in particular, we can always write it as some energy density times the integration over some n-2 set, right? So we've got something, a point in R2 or a line inside of R3 or something like this. And our defect measure, where things blew up, always looks like some energy density times the Hausdorff measure on the set that we're integrating on, right? That's what rectifiable really gives us. We call this set S that we're integrating on the blow-up set, and we call E of X the energy density, because that's basically telling us how much energy was actually lost. So in the last example, S was a point, and E was 8 pi, which is exactly what this says. I don't have time for a more complicated example. How am I doing? Terribly. Okay. So it turns out that at most points of a defect measure, we can blow up and see energy bubbles. So I'm going to begin with what's the only technical definition in this talk. So let's take a sequence of maps, Fj from B2 to n, and some fixed mapping B from Rm, right, the dimension of our domain here, and to n. That one's purposely from Euclidean space. We call F a blow up at some point x inside of our domain here, if there's some points there and some radii, so that when we zoom up on it, right, what we actually get is this limit f in the limit. So over here, the way you should be thinking in our last example here is that here's the point 0, here's our f sub epsilons. Our blow up here, f sub hat epsilon of y might be equal to f epsilon of epsilon inverse, no, epsilon times y. So if I zoom up around the origin on my example and I blow up that ball of radius epsilon to a ball of radius 1 over here, what I'm going to get is actually just the mapping, which is 1z for every single epsilon. So I'm just zooming up with a microscope is what I'm saying. And if you can limit that limit is called a blow up. In this case, you have a limit which is 1z because actually it's a constant sequence. And finally, we call B a bubble mapping if the following happens. If we can write Rm as being basically a two-dimensional harmonic map. So as we can write Rm as being Rm minus 2 cross R2. And if our mapping B is independent of the m minus 2 variables, it's only a function of the two variables. And as a function of the two variables, it's a finite energy harmonic map. You call that a bubble. And finally, we say that B is a bubble at some point x for the sequence if there's a blow up, which is a bubble. So in other words, if we have blow up occurring and we can look at that point, and if we zoom up on that point, we get a solution in the limit that's only a two-dimensional solution. It doesn't depend on more than that. Then we call it a bubble at that point. And Feng Lin basically proved that happens a lot. That should almost always happen. By the way, the word bubble here is because once you have a finite energy map from R2 to N, you can conformally compactify it to make a finite energy harmonic map from S2 to N. Hence the term bubble. You got your S2 in here. Yeah?
What makes it two-dimensional specific as opposed to an arbitrary sphere around?
Yeah, so no, it has everything to do with the fact that this blow-up set itself is n minus 2 dimensional. So what should be happening there is that if you're blowing up along an n minus 2 dimensional thing, then when you zoom up most of the time, it should be looking like an n minus 2 plane when you zoom up on it. And your solution should only be kind of in the other directions. So that plane should be like an invariant symmetry plane in the end. So it has everything to do with the dimension of the blow-up set. If the blow-up set was codimension 3, you should expect three-dimensional solutions to appear out of this. And I have exactly 1 minute left, and I have at least 10 minutes left, so I'm just going to have to zoom up here. Okay. And so our example, as we discussed from before from our sequence, tells us that if we take our x epsilon to be 0 and our R epsilon just to be epsilon, so exactly the same radius that we always sort of focus on. And if we blow up at that, then we get a constant mapping 1z. So it in particular it certainly limits, and we certainly get a bubble. And the reason we care about that, getting these bubbles, is that we can now reinterpret this. So remember our energy measure from these two-dimensional examples, it limited to 8 pi times the Dirac delta. This 8 pi isn't just anything though, it's now the energy of this bubble we had at this blow up. And the point is that that's not an accident. The amount of energy that got lost there, in this case it's almost a tautology because the entire harmonic map got lost. But the amount of energy that got lost at one of these blow up points was exactly the energy of a two-dimensional harmonic map that disappeared in this limit, a bubble that disappeared in this limit. And what Feng-Hua Lin proved was that at least at most points of the blow-up set, there are lots of bubbles. Like this is not like some random definition. The fact that you get these two-dimensional solutions does happen almost all the time. And based on the fact that Uhlenbeck and Taubes proved this for holomorphic maps and surfaces, the energy conjecture became the following. So for almost every point of the blow-up set, we had this energy density is precisely the energy of the sum of the bubbles that appear at that point. So for almost every point of your blow-up set, whatever that happens to look like, there will be bubbles, two-dimensional solutions that appear after you blow up, and the sum of those energies is exactly the energy density, exactly how much energy got lost. Okay, and okay. These are all the people who deserve to be named, but I'm out of time. So the theorem is that it's true, but I'll leave it. I'll leave it on that, right? So the theorem is the energy identity is true. And these are all the people that deserve namings. And if we discuss a little, I'll try to throw their names in while we're talking. Okay, thank you.
Any questions?
Maybe my question has already been answered before. On dimension 2,
Yeah.
why this does not happen?
Say this one more
On
time.
the domains of dimension 2,
Yeah.
why does this phenomenon not happen?
It does happen. So
it's also smooth to harmonic map.
So yeah, but these are all smooth, but they're blowing up at the origin, right?
Or the sequence.
The sequence is blowing up, right. Where this blow up is occurring is on a larger set than the singular set of any fixed harmonic map. That's the point. Conjecturally, one of the really good conjectures left here is that a stationary harmonic map should be smooth away from a codimension 3 set. People can prove n-2 measure 0 set, but they can't prove codimension 3. Basically because what we see from this example is that it's not effectively smooth away from a codimension 3 set. And analysts are very bad at proving something is true if it's not effectively true. So people really can't handle this just yet.
Got it.
Can you have a bubble out of a bubble?
Absolutely. You're going to bubbles on bubbles on bubbles on bubbles, yeah.
So what's the simplest kind of baby example to think? Like this is the example for a single bubble.
Yeah, exactly. So if I were to, I'm going to make numbers up because I have to get them right. I mean, but something to the following effect, you can maybe envision how this might look. So instead of like an epsilon z, if I did something like a epsilon plus epsilon squared z, no, I can't do that, can I? Z1, Z2, and then Z1 plus Z2, I don't know. I'm making this up. But the point is, if you do something like this, you might see one bubble appear before the other bubble because of how it's going down. Right? This may be wrong. I made those numbers up, right? But you can sort of envision how just picking the polynomials here with different powers of epsilon, some things will go away before other things. And every time something goes away, you're going to get a bubble out of this.
I actually had a sort of follow-up question.
Yeah.
So how do you keep track of just how many bubble, like you could do just got a little bit and you'll get a slightly different map, but that
Yes.
won't count as a different bubble, presumably.
Yes, that's
so
right.
how do you classify the ones that you want to count?
So in dimension 2, it's real easy because essentially every time you go through a bubble, you lose energy. In higher dimensions, this is vastly harder. Right. The first step to all this, which really sort of predates this paper here, is something called the quantitative annulus bubble decomposition. So you can decompose a general solution, right? So really, actually, what we prove is a very effective version of this. This energy identity statement is just sort of a consequence. There's really an effective statement floating around here that basically says just that most of the time when you slice, there'll be a finite number of bubbles that actually exist. So actually, a general two-dimensional slice will look like a two-dimensional solution, in fact. And so the first step is you've got to decompose your solution into pieces that look like bubbles and pieces that look like regions in between bubbles, which we call annular regions, right? And you've got to effectively bound the number of them. And then you need to see that most of the time in some effective quantitative way. Every time you pass through a bubble in one of these slices, you also bump up energy. So every time energy bump, then you can control the number of bubbles that appear. You don't know where they appear, but you can control the number that appear. This is a kind of what happens. And of course, there'll be a smaller content of regions where you have no idea what happens because there's more than just bubbles and non-bubbles in higher dimensions. But as long as you can say it's a small set, that won't matter. That answer your question?
I'm not sure if this is related to Jake's question, but like in the pseudomorphic case, you have this minimum possible energy which throws out like infinitely many bubbles. Do you have something like that there?
No. So that's very much a two-dimensional phenomena that you're talking. If I understood correctly, like essentially what you're doing there is you're trying to find the smallest bubble that way, but you can't really play those games in higher dimensions. Like that's just those games are because you can't easily rig up examples. In fact, one that I erased because we don't have time. Where essentially you'll have like some bubble appear at some radius, but as you approach the origin or something, so it's like a line of singularities that are occurring, but there's an actual singularity at the origin. The rest aren't singularities, they're bubbles, but those bubble sizes are shrinking as you go down, right? So if you try to play that game, what would happen is you would get an actual singular point, but on a codimension 3 set. So there could be a codimension 3 set where you actually, yeah. Once you get to higher dimensions, those that can actually shrink, you can't play those games.
Hi, Aaron. So could you have before I ask a question? So so your result is for any you have this this Fan Huanling's case, you have this blowing up measure, so the theorem is for each point, right? So the measure is given by a bubbles at that point.
For almost every point of the defect measure.
For almost every, so it's
it has to be almost every. So a similar example that here. Let me draw a picture. I don't know if can you see that? Can you see the whiteboard?
Not yet, but I guess depend.
So this is related to what we were just discussing a second ago. You can build an example kind of like this, where what's going to happen is your bubble is going to kind of occur here and then go down. So it's a like n-dimensional solution, and it's looking like two-dimensional solutions on each of these two-dimensional slices, but it's an actual singular point here, so the bubble size is shrinking as you go down. So that what happens at this point, there is no bubble, right? Just kind of everywhere else you get bubbles. So you kind of only have the bubbles almost everywhere when you're floating around this.
Mm-hmm. But that's depends on how you define the bubbles at that point, right?
That's probably fair. That's probably fair. For this example, that's true. I would say maybe what you're saying is right in general, but we don't even know. Yeah, there's too much there's too much small content that I'm throwing out here. I think that's probably a fair question. Yeah, I don't know almost every if we define it correctly. Yeah.
Another question is related to some people asked before previously. So I guess it's the type of bubbles. You can somehow stratify the blow up set according to types of bubbles, right? So the top strata maybe is top strata, and you can say it's maybe the simplest, most generic bubbles. For this is it possible to be that must be rectified by set, right? Or it's the rest is measure 0 or something like that. Sorry.
So the defect measure is rectifiable, but I don't think that's what you're asking.
No. Defect measure is rectifiable. I understand that. That's what Fan Huanling proved. So what I mean, so it's but if you stratify the defect set according to a type of bubbles, say only one bubble, for example, some maybe that's the most generic case. So if you stratify the defect sets according to a types of bubbles, so this
I think I understand.
rectifiability problem of strata. Maybe the simplest one is that clear? the top one is almost everywhere.
It's not clear, and here's why. So I don't think we wrote the example down, but I think we meant to, and they just never got around to it. So if the target in is analytic, then maybe. But if the target in is smooth, then you're going to be able to build examples where you have two-dimensional harmonic maps in it, so S2 harmonic maps, with a countable dense number of energies. And so even making precise sense of what you mean by the stratifying becomes very unclear, because you're actually going to have jumping all over the place, coming from the fact that you don't have discrete, it's not really quantization. You have a countable number of energies that can appear still. If the target's analytic, I think something like what you're saying sounds very reasonable. Although it would take some work to do. Maybe,
You probably need some assumptions. Either is the background metrics are analytical, or maybe it's for generic cases. You can also make a target generic or something like that, right?
That's right.
Target metric generic. So domain is hard to say. Bubbles does not depend on domain metric that much, but the target may depend.
Yeah. If you want a stratification of that, that's going to be rectifiable and compatible with the type of bubbles you get. Yeah, I think something like an analytic for the target's probably needed.
Mm-hmm. Also for generic, right?
If
a target is generic, because all these bubbles coming out from spheres, harmonic spheres in the target. So if a metric generic, these harmonic spheres are in a general position, maybe you can say more about this.
Yeah, I think that's right too. Yeah, that's right. Yeah, I mean, you can certainly stratify the defect measure and make all the pieces rectifiable. But to make that line up with how the bubbles appear, right, you need some sort of generic condition or analytic anyway. Something.
Any more questions?
Maybe I have a question. So in in solar maps, which is a similar kind of thing in dimension 2, you have the stable map compactification, and one way to interpret it is you have an energy blow up on a disk where you have various nested disks inside where you can control the energy. Is there a similar attempt to do? I mean, is there an attempt anywhere to generalize this to higher dimensions? So in RN, you have a ball. The energy blows up, and the ball is shrinking. But then maybe you can identify regions where you were kind of alluded to this in the discussion, right? That you have several bubbles at a point. But is there some finer structure to this?
Yes. So the first step to all this is the quantitative annulus bubble decomposition. This is an idea that really started occurring for a lot of the stratification theory for singular sets. So you can split up your solution in a very quantitative way into what you call annular and bubble regions, but they have a different flavor. Right? The annular regions are the size of the bubbles can vary around because it's higher dimensions, but it has that kind of flavor to it, defined correctly. And you do effectively split up into those regions, and controlling those regions and showing that those regions have finite energy is actually what this all kind of comes down to once you do that decomposition. I mean, so yes, that's like step one.
What is the shape of the region? Are these just nested balls or something?
No, it's more of so the actual definition is very long and painful, but like taking this example here that I have written on the whiteboard, an annular region would be this. So in this case, it would have to have some center, T, which in this case would just be this line that we have written here. And you need a collection of balls or just a radius function on it that basically says what the size of the bubble size is. It would go to 0 here. It would come out here. And then everything else is the annular region. So you see kind of on two-dimensional slices, it looks like a two-dimensional annular region as you go through. And if you kept going down inside, you could extend it and actually get, on two-dimensional slices, you'll get what you say. You'll get annular region disks, and then bubbles, and then more disks. But it's a global object that actually, you get that as a corollary, more of it. You get this global object that has that flavor to it.
Okay. So the basic picture is still like the two-dimensional picture? Is that what you're saying? Like in the normal direction, but then you have to...
In the end, it is. The thing is that these decompositions, these annular regions, even make sense for a higher codimension. They're used for the singular set stratification. So in the end, a result, basically the quantitative energy identity in the end will be the statement that most two-dimensional slices look like a two-dimensional solution. But that's what you get at the end. That's not really how you prove it. You get that as a corollary.
Okay, thanks.
Yeah.
Actually, this question reminded me of one thing with game. Why about this topic? There's some topological consequences. So I guess all you studied here are parameterized version, and have a good analysis of things around the singular set or blow-up set. How about the unparameterized version? For example, if I look at the pseudo-holomorphic curve near the singular pseudo-holomorphic curve, how do you parameterize things nearby? I mean, holomorphic case, purely holomorphic case is trivial because it's linearized. But for pseudo-holomorphic, it's if we have a more understanding about the things around the singular pseudo-holomorphic curve, that would be nice. But that's unparameterized version. It's simply harder than much harder than parameterized version.
So sorry, I lost the thread of what you mean by parameterized. You mean sequence? You mean taking a
No, I
family
mean,
of
if you look
modules?
at a minimum submanifold, for example, pseudo-holomorphic curve, you just look at unparameterized, right? Like a minimum two-dimensional minimum surface, let's say
Oh, okay, like a minimum.
in a
That's what you
Riemannian
mean.
manifold,
Okay.
and so you try to compactify it and the moduli space, or you get some singular ones. Then the question is around the singular ones, what can you do some analysis on that, some structure things, structure of a minimum surface around the thing, a structure of a modular space or minimum surface around the singular ones. Anyway, it's not directly related.
That's a next step question, I think,
also
right?
about the structures. So if, in a sense, around it.
That's right. So maybe what you're really asking is, so you prove this quantitatively. Do you prove it so quantitatively that you have some understanding of everything nearby? And to a degree that's true, to exactly what degree and to what you can say, I haven't quite thought through. Because it's certainly true that these decompositions, these sort of effective things, are going to be continuous nearby, in the right sense of the word. But exactly what that buys you, I'm not quite sure yet. I haven't really thought that through.
Any more questions? So I have one. Do you expect that there'll be like an almost stationary version of this, like in some sense of almost?
In the right sense of almost, I guess, right? I think there are two-dimensional almost where it doesn't hold, right?
Right.
And so say it correctly, yes, and say it wrong, no. Well, what that sharp line is, I'm not sure. I haven't thought about it.
Okay, if no more questions, let's thank Aaron again.
Thank you.
We'll come back at 10:30.